Okay, class, I'm going to focus on a new topic, which is actually related to two populations and the difference between two means for two populations. But we have a very special situation this time. That situation has to do with the concept of what we call match pairs or repeated measures. What we're talking about is a situation where we want to test the difference between two population means. But the sample that we use is a single sample that will give us repeated measures. So we often refer to the samples as being matched in the sense that we use the same elements or the same subjects in the study or in the experiment. All we do is we change the conditions. So say, for example, we were interested in testing whether or not a new device will improve worker productivity. So what we can do is, before training employees in terms of how to use that device, we could actually measure the performance on a series of tasks. So we would take a random sample of, say, 10, 15, 20 employees, so sample size N, and get them to do the task and then measure the performance. Then we train them with the new technique and then turn around and measure the performance again. And the difference between the two performances of the same individual gives you a measure of the improvement as a result of using this new technology. So the same individual gave us two scores, and hence the term repeated measures. So we were repeating the experiment. We got one measure before the training and then one measure after the training. So hence we call that repeated measures. And so even though we now have two samples, the two sets of data are related. One before and one after from each individual. And so we call that repeated measures, or the difference between population means with repeated measures. Interestingly enough, what happens is that we would focus on the difference between the two sets of scores, and the problem boils down to a single sample problem, not two sample problems where these samples were independent before, but rather two samples that are dependent. And when we take the difference between the paired scores or the match scores, we now have a single sample of differences. All right? So here's our sort of illustration of this. We have these two populations. We are interested in testing a hypothesis about the difference between two population means. HO mu1 minus mu2, and that could be greater than or equal to or less than or equal to 0, in which case HA would either be greater than mu1 minus mu2, greater than 0 or less than 0 or not equal to 0. So one of those three options is what we're looking at. But what we will do is we will define the difference between those two means as mu d. So let's call mu d the difference between 1 and 2. So what we would do, as I mentioned to you already, is that we would take one sample. Let's just say this is our sample ID 1, 2, 3, 4, 5, etc. up to n, and then we could call this before and after. So we get one score before, say 5 for example, a score after 2, 8, 4. This is just a random problem, and so on. 6, 5, 9, 9, 7, 4, etc. So this is the same individual repeating the experiment twice, giving us a score before the training, for example, or a score after the training. Right? So the effect of that training would be the difference between those two scores. So we would create a value which we call difference. So the difference here is 3, the difference here is 4, the difference is 1, difference is 0, difference is 3. So clearly those differences estimate for us the difference between the mean before minus the mean after. And when we take those values and we find a sample average, it is estimating that difference. So we could say that we have a mean difference, mu d, which is equal to the mean before the training minus the mean after the training. And so here is our single sample of differences that we would now take. We would now take that and calculate a sample mean, which we would call, we could call it x bar d, which would just be the sum of the differences, di, over n, and then sd, which is the standard deviation of the differences, which would be, we recall our shortcut formula, the sum of the differences squared minus the sum of the differences all squared over n, but divided by n minus 1, the degrees of freedom. So now we have the standard deviation. Now we have a sample mean. We could get a t-value, which is our test statistic, assuming, of course, the population standard deviation sigma d is unknown, will just be sample, which is x bar d minus population mu d over standard error, sd, because we don't have sigma, sd divided by the square root of n, the sample size. So this problem actually boils down to a single sample problem. And we could actually calculate the p-value and all of that stuff. Okay? So this is called hypothesis testing for the difference between two population means with matched pairs. The pairs, the pair of samples are matched. Now what we did before was that was actually referred to as the difference between population means, but independent samples. We did not have repeated measures. So I could have said, let me take a random sample of individuals before the training and then measure the performance. Then grab another random sample after the training and then take their scores. So those would be two independent samples. In which case, if that were what we were dealing with, we would have to treat it this way. T0 is x bar 1 minus x bar 2, mu 1 minus mu 2 over S1 squared over N1, S2 squared over N2. So that's how we would deal with that if we're talking about independent samples. But just to reiterate, when the samples are dependent now, instead, because they are matched, what we do is we calculate a difference, which we will call DI, which be the difference between the score for sample 1 and the score for sample 2. And we call that DI, all right? And then if we take an average of all of the sample differences, if we take the average of all of these sample differences, we will just sum the differences, divide by n, and we can calculate the standard deviation of all of the differences. And it would be what I've already mentioned, okay? Which is sum of di squared minus sum of di all squared over n divided by n minus 1. So we have that. And so then our t value is just x bar d for the differences minus mu d, which we will define mu d as mu 1 minus mu 2. Okay, mu 1 minus mu 2 over SD, standard deviation, divided by square root of n, standard error. So there you go. All right, so let's actually work a problem and see how that turns out. Here's a sample problem right here. A market research firm used a sample of individuals to rate the purchase potential of a particular product before and after the individuals saw a new television commercial about the product. So before the commercial and after the commercial. And we want to know whether or not that commercial actually influenced their behavior, all right? So the purchase potential ratings were based on a 0 to 10 scale, with higher values indicating a higher purchase potential. The null hypothesis is stated that the mean rating after would be equal to or less than before. Rejection of the null hypothesis would show that the commercial improved the mean purchase potential. In other words, it will show that the mean after is higher than the mean before. If it improved it, because we said higher scores mean higher likelihood of purchasing. So we want to use alpha is 0.05 and test whether or not the commercial was actually valuable in increasing the purchase potential. So essentially what we want to get, or what we want to assess in terms of hypotheses, is that HA, our research hypothesis, is that mu D, which we will define as mu1 minus mu2, let's call it mu after minus before, so after minus before, is greater than 0, because after, the purchase potential is higher. So that should be greater than 0. So if the commercial had no effect, then the null hypothesis would simply be that mu D, the difference between those two means, would be less than or equal to 0. In other words, it did worse or the same as before. All right? So that's kind of what we have. So let's test this hypothesis, and we're going to set it up with our 5 steps. So step 1, the hypotheses. All right? So what we will say is that the commercial was valuable versus it was not valuable. So HA, commercial was valuable versus the commercial was not valuable. Now, if the commercial was valuable, that means the mean difference, which I will define as mu after minus mu before, mu D will be greater than 0. And then if it was not valuable, then mu D would be less than or equal to 0, defining mu D as the mean after minus the mean before. So that's step 1. Step 2, the test statistic. The test statistic would be T0 observed, I say 0, but it's actually TO observed, is my sample estimate, which would be given as X bar D minus the mean, mu D, over the standard deviation divided by the square root of n. And the reason why I'm using SD is because I don't know the population standard deviation. Now, our degrees of freedom is not that crazy degrees of freedom formula. It's simply n minus 1, because we just have a single sample to contend with. So that is step 2. Step 3, we need a decision rule. So this is no different. Since we are looking for evidence that the mean difference is greater than 0, it means that we have a right tail test. So if T observed is greater than T critical, greater than or equal to T critical, right? Reject HO. Otherwise, we fail to reject the null hypothesis. All right? If the observed T value is less than the critical value, then we would fail to reject HO. Fail to reject HO. All right? So what is that critical value? That critical value, because it's a one-tailed test and alpha is 0.05, then basically our T critical is T 0.05. And it turns out that we have how many values in our data? Let me just go back and see how many values we had in our data set. I believe we had 8 values in the data set, which means that our degrees of freedom would be 8 minus 1, which is 7 degrees of freedom. So it would be 0.05, 7. Whatever that value turns out to be, we'll find that out later, okay? Or, if the p-value, because I'm going to use the p-value approach, is less than 0.05, we will reject the null hypothesis. That's step 3. Step 4. So now step 4, we need to go ahead and find the differences and then find the sample mean and the sample standard deviation. So we do it this way. Before, we have 6, 5, we have 6, 4, 7, 7, 4, 3, we have 3, 5, we have 9, 8, we have 7, 5, and then we have 6, 6. So now we're going to create a third column of our differences, our DIs. Okay? Let me just put it in small letters as opposed to capital D. DIs. So I'm going to actually do DI will be x after, minus x before. That's how I'm going to calculate my difference. So that's 1, that's 2, that's 0, that's 1, negative 2, 1, 2, and 0. If I add that all up, the sum of those values turn out to be 5. And then if I square these values to get my x squared, this is 2, this is 4, this is 0, this is 1, this is 4, this is 1, this is 4, this is 0. If I add this up, this turns out to be 15. So the sum of DI is 5. The sum of DI squared is 15. And so I could calculate SD and D bar, and X D bar. Sorry, X bar D, my apologies. So I could actually calculate the sample mean and the sample standard deviation. So X bar D is just 5, it's not 15, but 5. The sum is 5 over 8, which is 0.625. SD, I think I need to kind of squish this now. SD would be 15 minus 5 squared over 8 divided by 8 minus 1. And when we take the square root of that, it turns out to be 1.30. So now I could calculate my t-value. So this was actually step 4. I did not name it, the analysis. So t observed is x bar d, the difference, the average, the mu d, sd over the square root of n. So our sample mean difference is 0.625. HO will give us the value of mu d, which is 0. If you go back to HO, you will see from the null hypothesis here that we're going to set the difference to 0. And then the standard error is 1.30 over the square root of 8. It turns out that this value is equal to 1.36. 1.36. All right, so now we need a p-value. Because this is a right tail test, the p-value is, all right, so p-value let's go back here. Something strange is going on. So here we go. The p-value is the probability of t being greater than or equal to 1.36. Now, why do I say greater than or equal to 1.36? Because it's a right tail test. And so our sample value right now is plus 1.36, which is in this region. And so that will be our p-value right here. Well, if we look up the table, it turns out that this value, p-value, and we don't have to multiply by 2 because it's a right tail test. It's a one tail test. is between 0.1 and 0.2. Right, between 0.1 and 0.2. And so as you can see, this p-value will be greater than alpha, which is 5%. Right now, the p-value is between 10 and 20%. If we actually use Excel, and the formula in Excel is that you would have to use t-distribution, t-dist, and there is t-distribution t, and you just provided the value, which is 1.36, and you give it 7 degrees of freedom. It will give you what the exact value is, and I believe that exact value, I don't have Excel up right now, might be 13%, 13.02%, 0.1302. I believe that's what it is. I could be wrong, but I believe that's what it is. And maybe you could verify that for me by just simply plugging in that function in Excel. All right? So, but at least we know it's between 10 and 20%. So now, step 5 is our decision conclusion. 5. Decision conclusion. So since the p-value is actually greater than 5%, which is alpha, we fail to reject HO. What do we conclude? We conclude that the commercial, right? There's insufficient evidence that the commercial was valuable. There is insufficient evidence the commercial is valuable. All right? And then there's a possibility of type 2 error. We don't know what it is, or we know that there's a possibility of type 2 error. So that basically is the problem in a nutshell. All right, so just to revise and let's recap, we actually were looking at the impact of a commercial on the likelihood of buyers to purchase. So we actually allowed the participants to view the commercial, and then we first measured their likelihood to purchase before they actually saw the commercial, and then we measured it after. So since it is the same set of individuals before and after, that makes it a match pairs or repeated measures test. And so we had 8 participants. The population standard deviation is unknown, so we're going to use the t-distribution. We calculate the difference between the 2 scores, and we get a single sample of differences. That single sample now represents the sample of differences, and so the average of those will estimate the difference between the 2 population means, mu after minus mu before. We then go ahead and find the sample mean, sample standard deviation of the differences, and we compute the t value, which is the test statistic, by taking the difference between the sample difference and the population, which we actually set to 0 in this case from HO, and divided by the standard error, which is SD over the square root of n. That gave us a value, a test statistic of 1.36, and it turns out that that test statistic was insufficient to reject the null hypothesis. Why? Because the p-value associated with that test statistic was between 10 and 20%, which is higher than the 5%. So as a result, we have to conclude that there is insufficient evidence that the commercial was valuable in that it actually persuaded people to buy at a higher rate. And so we then have the risk of committing a type 2 error, failing to reject the null hypothesis when it is false. But clearly, the problem shows that there is insufficient evidence to reject the null hypothesis. So that, folks, is a repeated measures paired difference test. Okay, repeated measures or paired difference or match pairs Those three terms are used interchangeably, and I hope you do understand the process. So now I would like you to try the problem that comes after that on your own. Follow the example that I just did and actually do the next problem, which is problem number 27, the one that immediately follows that particular question. Have fun, and I will be with you with the next video on the difference between population proportions. Thank you.